Hello everyone, my name is Vikas Soni and I welcome you all in this fifth lecture of our DP playlist, and in this lecture we are going to learn about Knapsack DP. So I hope that you are enjoying the playlist till now and hope that you will enjoy it in next videos too. So what we are going to learn in this video, so it is going to be about Knapsack DP, and in this we will learn what is the Knapsack DP, what is the use of it, and why we can't use some greedy ways, and like the main part of it is going to be all learning about all of its variations. So variation are like unbounded knapsack, then bounded knapsack. The bounded is also of two types. One is a simple 0 1 knapsack, and one is a limited knapsack when you can use some items of some limited types times. You will learn that later, and you will also learn about the subset, some DP, and some other techniques too. So, like briefly speaking, it is going to be like the knapsack DP is like a very fundamental topic of DP, and it's like there can not be like more out of the box thinking questions. So like you have to learn this fundamental algorithms and techniques, and like most of the questions are just a slight variation of this type of DP. So this is yeah, important topic, and once like I guarantee you that after this video, the 99% so problems of this type of knapsack DP will be solved by you. So let's start learning the knapsack DP with a simple question. Okay, so this is a most fundamental question of this knapsack DP. So assume that there are several items. Okay, and assume that you are some robber, and there are several items in the store. So let's say there are items, okay. So the items have two things, right? Items have their weight, and they have some values, right? So let's say you see something. Okay, let's say the item one have weight is equal to 2 kgs, and it values its price is like 10. Then item 2 have, let's say, 5 5 unit of weight, and its value is 3. Then item 3 has some weight. Let's say it's weighted also, maybe let's say this thing is 30 and this thing is 25. Okay, let's say this is the thing, and you are robber. So you have a bag. Okay, so your bag has capacity is equal to, let's say, 5 units only, right? So now for each just a second. Okay, so like for each item, you can either take it or not take it, right? Or not take it. So if let's say if you take this first item, then your bag will have 2 kgs of weight, and you will gain the 10 units of value, right? And if you take this item 2, then you will get 30 units of value, but like your bag will be stored now 5 kgs of weight, right? So you have to now, like in this, according to this your bag's maximum capacity, you want to find the some sequence or some subset of items that gets you the maximum value, right? Okay, so let's say you are rubber and your capacity is only 5 units of weight, right? You can take, let's say you can take only 5 kgs of items, right? And there are 3 items. Okay, so now uh okay, just a second, I did some mistake here. Okay, so now let's say if I was a rower, okay, and I see that my bag only has capacity of 5 kg. What should I take? So like the one option is like I take the item number 2 only. Okay, if I take item number 2 only, then my value, the money I get will be 30. Okay, or the other thing is I can take item number 1 and 3. So now my weight in my bag is going to be 2 plus 2 is equal to 4 kgs, which is right. My bag is have capacity of 5 kg, so I can have item 1 and 3 both. Okay, and now the value I get is 10 plus 25, which is 35. And yeah, it is the best option, which is more than this 30. So this is the optimal answer for this. Okay, so like if I was robber and if I have bag which have 5 units of storage, so I will take this one and this three. So like this, okay, so this type of question is called a knapsack, and now you have to find the optimal answer for this. So what should be the optimal answer? Okay, so let's say if I can take items in fraction of type, right? Like I mean, I can take this, like if this value is have this 5 kg weight and the value is equal to 30. So I mean, if there is a way that I can break it in 2.5 kg and take value of 50, if this type of case, what I will do is I will just get the item with most okay, like okay, I'm talking about the greedy way. Okay, so the greedy way is like take the one, take the one which have the maximum value per kg, right? This is fair, like by thinking. So like in this case, this one have values you 5 units per 1 kg, right? This thing have value about 6, let's say 6 rupees per kg. This thing has the most value, which is 12.5 rupees per kg. So yeah, the best thing would be just you take this one of this item. After you take this, then you will see and get this, right? So like if you can take in fraction, this is going to be the best way. But yeah, we have to take whole, right? The case is only that either take full or take nothing, right? Or take nothing. So this is the type of problem we have currently. So therefore we have to think something. So again, like just pause the video for 2 minutes and try to think how you are going to solve this. Yeah, one thing is sure that you are going to solve it by DP. The other thing is sure that the DP would be something like DP of I, where I will show you the from first I index, I mean from first I values, and there are going to be some other states. Okay, so like you have to think for this thing, like what should be the other states here. So for that you have to think what other data you need. So just take some moment and try to think in that way. So guys, I hope that you have watched the video and think for some time. Okay, let's just think what should be the brute force way in this question. So again, just copy paste this thing here. Okay, just a second. Like in the brute force way, it is you will understand what should how should the DP will look like. Okay, so let's say, okay, initially we will store that how much capacity you have and what is going to be the case, right? So let's say in the starting you are at the index number 1, and now you have a capacity is equal to 5 kgs initially, like because the capacity of our bag initially is 5 units, and I have not, let's just have kg as a unit, and I have not taken anything in my bag now. Okay, so this is the case. Now there are two options. Okay, either I can take this first value, first item, or I cannot take. I don't take this first value, first item. So what is going to be the two cases for this? So let's say I just take this. I take this. So if I take this, so now I am seeing about the, I am at the second item. Okay, I mean the case of the first item is now done. Now only have to think about the second item. And how much capacity I have. I have how much capacity I have now. So like the capacity is what I have taken the weight was 2 kg, so now I have 3 kgs left. And if I don't take, if I not take, then just I will equal to 2, and my capacity is just as it was previously, which is 5 kg, right? Because I have not done any changes. Like again after this thing, I can choose or not choose. I can either choose or not choose. Okay, and according to like this, now my thing will again changes. Okay, I is equal to 3, which will be same here too. Like what is the case? Items is equal to 3, so I will be equal to 3, and let's say in this case capacity will be, okay, I cannot take this thing. Okay, I cannot choose, so this way is not valid. And if I not choose this, then again capacity will be 3 kgs. Okay, so you can see that here it is some type of exponential brute force, right? Because for each item there will be two options that I can choose it or not choose it, and it is going to be exponentially growth. But you can see that there may be some things which are repeating, right? Let's say like here, this is I equal to 3 and capacity is equal to 5 kg. There can be I is equal to 3 and capacity is equal to 3 kg. And now here you can just see that this both things are repeating. So like from this thing you have to, you can see the observation that maybe there's in some way you can find the value of this case, right? These both are the state. This is the, this was the observation, right? So from this you have found the states. The state is going to be I and the capacity, and the capacity. Or instead of capacity, like the better way, the thing would be the weight we have taken till now. So it's just the initial capacity minus the capacity taken. Okay, just forget this also. Yeah, just assume that it is a capacity. Okay, so like this both are the states, right? Because from this we found that some things are repeating, and so therefore we can just make some DP and just think for this. So how the states are going to be? So state will be DP of ij, DP of ij is equal to from first I element, from first I element of what is the maximum, what is the maximum value we can have if the weight weight is exactly j units, right? So this is the case, like from the first I element I need that the, if the weight is just a j units, what is at most j units, then is at most, well then what is the maximum like value we can get. So this is our AP. And now how we are going to transition, right? Let's say you have the previous data. So now how you are going to find the value of current item. So I mean what I'm saying is that let's say you have the values of all of dp of I minus 1, dp of I minus 2, all of that stuff. Okay, I mean just weight is just think of ij, yeah. Then from this, how you are going to get the value of I and j? So this is the thing now you have to think. And this is a nice question. Okay, so and if you can solve this question, if you just understand this question, then again, like the 90% of this video is done for you, because this is the main thing. Okay, so now the states are nothing but, let's say you have found all of the values, right? And now you are at the ith element. Okay, so just assume that there are several elements, several items with 1, 2, 3, 4, 5, 6, 7. So what were the option for you? Just see in the brute force way. If you were at some point, then what were the other way? There are only two options. Either you can take this current element or not take this current element. That's it. So now this is the thing you have to think. So now, oh sorry. So now let's say you want to find the DP of ij. Okay, DP of ij. And for the ith item, item is equal to I. Let's say its weight was equal to wi, and its value, the value it give is equal to vi. Okay, so now there is one possible way that you didn't take the current option, you didn't take the current value. So now this weight is just same is equal to dp of I minus 1 j. Is that right? Or like instead of this j, let me write w. No, I should not write. Okay, so just try to think in this way. Like uh how should I explain this? Okay, so like I mean that if you don't take the current element, so then the result will be same, like for the first I and for the first I minus 1 elements. Okay, like if you don't take the current element, that it means that the weight is equal to j was made from the I minus 1 element, from the first I minus 1 element, because you are not going to take this current I. That is the thing. Or what is the other thing that you do? The other thing you can do is you can take this current element. So if you take this current element, then what will happen? So let's say there were several items. Okay, 1, 2, 3, 4, 5, 6 till let's say I minus 1. Then now it is I, that is I plus 1, and so on. You have to find the answer for this one. And it has weight is equal to wi, and value is equal to vi. And now if you take this current item, so now if the total sum was j, and if you have taken this wi, like you have taken this ith element, so now you got the weight wi from this I element, right? So can you say that, can I say that from this previous I minus 1 element, I should have taken the elements which weight is equal to j minus wi. Can you say this thing? Why? Because let's say from I minus 1 elements, I get this weight, right? I have the values which have weight is equal to this thing, and now after this I take the ith element which have weight is equal to wi, and now the sum is equal to total j, right? Which I need here. Okay, so this was the case. So this thing is like, so which means that I ask the question here, that what is the maximum value I can get if from I minus 1 elements I take the elements which have weight is equal to j minus w of I, which have j minus weight is equal to j minus w of I. What is the value I get? So that value I will get here also, right? Plus there is some extra value I will get. The extra value is because of I am taking this element, because if I am taking this element, then I will gain this vi value now. So therefore this is plus vi. and like I will choose whichever the maximum of this is. Okay, that is just the transition in it. So what I do is that, like, let me just let me just say what the DP thing is saying. Okay, so this DP of ij, what this thing is saying. So it is saying that from this first I elements, what is the maximum value I can get? What is the maximum value I can get if the sum should be equal to j, or the sum of weight should be equal to j, right? And there can be many possible ways for which the sum of items will be exactly j, right? There may be some case that I do this second, fourth, and fifth, and this their sum is equal to j, or I can take 4 and I minus 1, their sum is equal to j. But I will take with one way which gives me the maximum value, right? Because like there are going to be many possible ways to get the subset which is sum is equal to j, but I want to maximize my value, so therefore I will take the case with which gives me the maximum returns. So that was it. Now this value is equal to dp of I minus 1 j, which is nothing but I don't take this one, and now this is just the question of for this case, for 1 to I minus 1, because I know that I am not going to take this ith element, so therefore all of this sum is equal to j will be made from this first I minus 1 elements only. So therefore, instead of for the first I elements, I ask only first I minus 1 element, that what is the maximum value I can get from this first I minus 1 element such that the sum is equal to j. Or the other thing is that I take this element. So now I already got the wi weight. So now I ask the previous dp that what is the maximum value you can get if I want if the weight is equal to if the weight is equal to j minus w of I. This is the thing. And now whichever way is better, whichever gives me the better result, I will choose that one, right? So I will see this case, I will see this case, and from that I will decide if I should take this one or I should not take this one. So this was this DP. So let me just have it on table, and after that you will see it in detail. So let's take some items. Items are 1, 2, 3, 4, 5. Let's have their weight. Let's say their weight is equal to 5, 2, 1, 6, and 4. And their value they give is it is, let's say, 3, then 6, then 4, then 1, then 2. Okay. So now from this, okay, let's have it less. Let's just make weight is the weight is pretty big for me. Weight is 1, 1, 3, 2, and 1. Okay. I hope this is better. So now what we will do is that we will make a table, make a DP table, right? DP of I and j. This thing is our index, and this thing is the weight, right? Right, for some weight, what is the maximum value I can get? So this is the weight. Now what can be the maximum possible value of this weight? So like you can see that 2 plus 1, 3, 2 and 1, which is going to be 6, 7, 8 and 9. So yeah, the maximum units of weight I can make if I take all of this is just 9. So yeah, in my states of DP, this J value is from 0 to 9, and this I is just index, so yeah, it is going to be till 1 to 5. So let's just make the DP table accordingly. So let's have the weight here. and let's have the index here. Okay, so index are like 1 2 3 4 and 5, and the weight are 0 1 2 3 4 5 6 7 8 9. Okay, let me separate it. Okay, like just wait a second, and after this example you are going to understand what this thing is doing, and after that I will also explain you the intuitive version of this thing. Let me just remove this index here. This is looking better. Let me have this one here. Okay, just wait a second for the this is index. Okay, so now, okay, let's say like if I take this, how should be our DP table should look like? Okay, so let's say from the index 1, what if I take the weight is equal to 0, what is the maximum value I can get? So like my if my bag is can store the like my bag has capacity is equal to 0, I can store nothing. So yeah, the answer will be just 0 here, right? Then then let's say if from my index 1, okay, from this just this first index, I mean from the first item, if my bag has capacity of exactly 1, okay, so like from the first item I have to take the items which have weight is equal to 1. What is the maximum value I can take? So like yeah, from this first one items from this first one items, and you will see here that the weight of first item is 2, so I cannot take it. So then this thing will be 0. This is nice here. Okay, so let's say from the first one index, if I want the weight is equal to 2, then what is the maximum value? So if my weight is equal to 2, I will just take it, and now my value is 3. So this is 3. Now we come here. From this first item, if I want my weight is equal to exactly 3, then what is the maximum value I will get? But you will see that the maximum value I can make is just 2, because either I take it or not take it. That's the only case. So I cannot make the weight is equal to 3. So yeah, this will be same for all of them. Okay, because this thing is, if I take the weight exactly j, right? So now comes the good part. Now the thing is like this. Okay, now from the first two elements, this is saying from the first two elements, if I want my weight is exactly 0, then what is the maximum value I can get? So this thing is also 0, right? Now for this weight is equal to 1. Okay, so yeah, now comes the good part. So from this you will learn a lot. Okay, so let's say you come here at from this index 2, and weight you want is 1. So now what you can do is that weight is equal to 1, right? So now let's say you will check if you can take this current element. Okay, so just see here. Okay, the one way is that you don't do anything for this in this second index. You just don't take the item at this second index. So now that whatever the thing was here will be same for here. Okay, so you just check what is the value here, right? This is the possible way. This is the one possible answer. Okay, so if this was 4, then this was also be 4, right? Because in the first index, if you can make the value is equal to, I mean weight is equal to 1 of something, let's say it is x. So what you will do is that you will not take the second index, and you will do whatever the way you did it to get here x, right? I mean you will see here. Okay, and what is the other case? The other case is that you take this value, you take this element. So if you take this element, then the thing is that you will get this value is equal to 6. But now the one one capacity is just lost to have this item, right? So now from the I minus 1 element, you have to find the what j minus this w of I, right? So the j is equal to 1. Okay, so the total weight is 1. The total weight is 1 minus the weight of this current item is also 1. So 1 minus 1 is equal to 0. So this thing, okay, this weight, sorry, this dp of 2 and 1 is equal to, either you don't take this one, so it is dp of 1 and 1, right? Or sorry, it is max, or it is max of these two values, right? Or what you do is that you take the current element. Okay, and if you just a second, what is the problem here? That means, so it is max of, either you take you don't take the current element, so which will be I minus 1j, or you take the current element, you get the vi point extra, vi value. But now, like, you have to ask that from I minus 1, what is the value I can get if I make the, like, if I want the weight is equal to weight is equal to j minus w of I, right? That's it. So for this dp of 2 1, this thing will be maximum of dp of I minus 1 is 1 and j is again 1, or what, so the value, the second item give is 6, so 6 plus dp of 1 and 1 minus 1 is 0. This is the case. This value is 0 and this value is 6 plus 0, 6, and this is 0, so yeah, 6 plus 0, so this thing will give me 6, so this thing is 6. So which means that like, either I don't take this value, so now this thing will be just this, and I take this value, so I get the 6 point, and like from the I minus 1 I get the 0 weight. This was the case. So like this is 6. Now again, like, I come here, I check if I can just copy this, or what I do is that I will check this one, right? So for this, the answer will be 6 again, and yeah, similarly I will just fill up the whole table, and that's it. Okay, so let me just see the code here and you will understand everything. Okay, this is a bad one. Just a second, let us just write here. So let's say I have the input of the, let me just remove this. Okay, so let's say I have given what is I have given n and then x, and then for each integer I have given h and s. So h is the price of each book, so instead of weight I have given the price, and instead of value I have given the number of pages for each book. So in the starting I have n and x, I take the value, then I have two vectors, the one vector of let's say weight and the other of value. Then I take the input, Okay, so I have now taken the input and now I want to make the DP. So the DP will be like 2D DP for LL, and now the first thing is index, right? So this thing will be n or n comma what? Uh, and the other thing is the sum of this weight. So I have to see what can be the sum of these weights. So like this S is still 1000 only, and there are 1000 of it. So I can just have maybe okay. I just count the sum and okay. So what I do is here is that I just count the sum. Okay, let's say the sum is equal to, let's write here. Is there some problem? Why I'm not getting this function? I have to check. Okay, let's just count the sum. Okay, so like what I do is I run a loop and I just count what is the sum of this, all of this weight. Okay, I just add it. So okay, and now I know that the sum will not exceed this thing. So here I write that this thing will be like sum plus 1. Sum will be, I mean the weight can be from 0 to this till this sum. Okay, this is correct, and all everything should be initialized with 0. Now what should be the base case? The base case is nothing but dp of 0 0 is 0, and dp of 0 and w of 0 is equal to v of 0. Okay, so what is this thing? So this thing says that like from the first 0 elements, or if you just see the case for like one based indexing, this is a 0 based indexing. Okay, so like till the elements till 0 index, if my weight is equal to 0, then the maximum value I can get is 0. And this is like simple, right? If you don't, like if you cannot take any element in your bag, then your maximum value you get will be 0. Or what you can do is set dp of 0 and w of 0, which means that from the first 0 element, if you take the element with sum is equal to this thing, then the value you will get is this one. That's it. After that, you just have to run a loop on the first index till the last, and then you have to run a loop on the indexes. So the weight is varying from 0 till sum and j plus plus. Okay, so now again, so like dp of I and j will be same as dp of I minus 1 j, right? And if you can take the current element, and how you are going to decide if we can take the current element, which is that if this value j, right, the sum you have, if it is like greater than or equal to the weight of this ith element, right? If this is the case, in that case only you can take the current element. So in this case, it will be maximum of dp of I minus 1 comma j and dp of I minus 1 and j minus this w of I, and the extra cost you will get is extra value you will get is vi. So yeah, this is the case, and let's just print the values. Okay, so this is a bit wrong. Mistake should be okay. This looks correct to me. Let's run this code. Okay, yeah, I did the mistake here. So let's have the input as we discussed in this question here. So let's say 5 and let's have the stacks equal to 3. The weights are 2, 1, 3, 2, 1 and the okay again there is a mistake. Okay, yeah, this thing should be of size n. This also of size n. So 2, 1, 3, 2, 1 and 3, 6, 4, 1, 2. Okay, this is the value we are getting. First I have to check if there is some problem in this or not. So the weight is still 9 only. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 0 to 10, which is correct. Then why am I getting extra values? Just give me a moment to think about this thing. This thing is also correct. So, okay, yeah, this is correct. This is correct. Okay. Yeah, this thing is looking bigger because there are two digit number here. But don't worry. So, like any point you can see here, any point you can see, it says that let's say this is I is equal to 2 and weight is equal to 0, 1, 2, 3, 4. This thing is saying that from the first three values, if my weight should be equal to 4, then what is the maximum I can get? Right? If my weight is equal to 4. So like it is that from the first three elements, if my weight should be equal to 4, what is the maximum value I will get? And the answer is that you will take these two elements, 2 and 3. The weight is 4 and the maximum you get is 10. So that's how you get the answer for all of these values. Okay. And again, you can see that there are some imperfection. Why? Like, why this 13 and then when the weight is bigger, you get only 11? So this thing is because you want weight is exactly as that much. So therefore, like, that is not so, like, when you want some answer, okay, like when you want if the weight should be exactly is equal to x, then it is just dp of I and x. But if you want the weight as at most x, it should be maximum x, right? So then you have to just see what is the maximum answer from whole this range, okay, till x. So from weight is equal to 0 till x, you have to get the answer, and whatever is maximum it is the answer for you. So that's it in this case, and I hope that you understood this thing. And again, you can just like optimize this, I space optimize this case, and in this case, yeah, you have to do the space optimization. So just see in this code, like here I have make the two vectors, the previous vector and the now vector, and because you know that for each value, okay, so like So like when you are solving the values of this row, the only row you need to know is this one, right? So therefore what you do is that you take the previous element and you have this current element, you count all these values, you store them. I mean, like if you want, you just use them. Now after that you make this element as this row as previous, and now this is current. So from using this you count this thing, and like yeah, that's how we do the work. And that's it. So just see that now of j is equal to previous of j, and if j minus h of I, so this is nothing but the w of I, the weight. If this thing is greater than 0, then it is just this one, and I just output this answer. So now of x is nothing but what is the max answer I can get the the what when my what do we say when I want the sum weight is equal to exactly x. So that was it in this question, and I hope that you understood this thing. Now what if you can take anyhow elements you want? Okay, like eh, like here what we talk is that either you can take this one or you don't take this one. But let's say there is no limitation on how much time you take this element. So like you can take this one times, two times, three times, four times, any times you want. Then what? It is called the unbounded knapsack. Okay, it is called unbounded knapsack. So there is no bound on taking some elements in your bag. Okay, so like in this case, just think for some time. Yeah, post this video. Okay, so like in the first thing, it is slightly harder to get the answer because like you don't know how to get this. But so the thing in this is that let's say what we did here, right? What we did here, we took it for one time. But yeah, you can say that you can do it for some other types, right? So what you can do is that you can run a loop, right? So run a loop like what you do is that while finding the answer, what you do is that you check, right? So like initially what we check only two cases. The one case is we don't take this one and we take this one. But instead of this, we run a loop here. Like loop is just until the total weight is so like say that while total weight is less than the max weight. So like till what we do is that let's say I take the current element, I take the ith element for one time. Then I check what is I take the current element for the I minus I mean two times, and then with I check the answer for this dp of I minus 1 and the j minus 2 times w of I, right? And the value I get is 2 times the v, right? Because I have taken this value 2 times exactly. Now I can take it 3 times, so like now the weight I have to take from the I minus 1 element is j minus 3 times this, and the extra value is 3 times v of I. So you can run a loop something like this, but now this will have you time complexity of O of n cube. Why? Because there are already two loops here, right? There are already two loops. One is still n and one is still sum, total sum. And then again, if you have this type of loop, it is going to be bad. But the thing is that here, let me like write a small line and you will understand this thing. The code, okay? So now in the bounded one, in the bounded knapsack, in bounded, like if I take the ith one, if I take the ith value, if I take the ith item, that, and I am talking about like the from first I items, okay, from first I items. Now, like I want some answer from the first I items, and if I take the current I item, sorry, if I take the ith item, then I know that I cannot take that item again. So like I have to check. I can't take again. I can't take it again. So I have to check on for first I minus one, right? Like, can you understand this thing? So let's say if I want to make some sum is equal to W, and I have taken this ith item one time, and I have got the value from this ith item, but now from the first I minus one item, I have to do other work, right? But here in the unbounded one, there is no restriction. There is no restriction. So even if I take from this, take from, even if, sorry, even if I take the ith item, I can take, I can take again from first I elements. Okay, so what this thing is mean, right? What does this thing mean? So like initially, let's just assume this thing again. So let's say this is the case, and 2, 3, 1, 2, 5, 4. Okay, so there are three items with weight 2, 3, 5, and the value is equal to 1, 2, 4. Okay, and now like you want that like the from the first two items. From the first two items, you want what, let's say, what is the max value you can get if the weight is equal to 10. Okay, so now if you take this one, if you take this one, like, okay, so just okay, we want the DP of from the first two item, the weight is 10. What is the max value of it? What is the maximum value you can get? You have to find this. So if this was unbounded, this was, sorry, bounded knapsack, then you can just take this one, and now you have to think for the other thing, right? So like if it was bounded one, this thing would be dp of 1, and 10 minus the weight of this is 3, right? You can take it only once, but like if this is the unbounded one, and now listen this carefully, and if this is unbounded one and I take this item, I take this second item once, then again there is no restriction in the range, right? Again, now again I have to choose from this first two items, because I can take the second item again. So yeah, this is the thing, and but now here the answer will be just 2 and 10 minus 3. Yeah, so that is the thing. So now here my dp of 2 and 0, sorry, 2 and 10 will be one case where I don't take this one. So if I don't take, it is 1 and 10, and if I take this, sorry, it is max. And if I take this, then again I have this range, like the range will be like 10 minus 3. Okay, so like this is asking that from the first two item, what is the maximum value I get if the sum is equal to 7. So that is just the change of one line here. Okay, so that's just the small thing I have to change is this one. Instead of dp of I minus 1, I have to do the dp of I, and that's it. And by just one change, I will get the answer for this bounded knapsack. Okay, So this was it, and now the time complexity also is reduced to O of n cross the sum. But initially it was like around n cube or something, right? So this will be bad for us. So just see that how by a small change we have reduced the time complexity a lot. Sorry. Okay, so okay, yeah, this is my favorite question in this till now, right? In this, you will learn a amazing technique. So now, like we talked about bounded knapsack, where you can take one item only one times, right? You can either take the one item or you don't take any items. And we also see the case for the unbounded knapsack, where you can take each item any number of time. Okay, but let's say in this question, this okay, where was it? Okay, yeah. In this question, like there is a limit. Okay, there is a limit on every item. So the limit is like you can take the second item only 6 times. You can take the third item only 2 times, right? So like there are the several copies of each book, and you have also given that how many copies of each book are there, and you have to find it. You have to find the answer for this thing. Okay, so now how the answer would look like. Again, like pause for some time and think for it. Okay, so like I hope that you paused it. So we will talk about the most easy way, or the most fundamental, let's say, brute force way someone can think of. So it is just like if I have that, let's say, some items. Okay, if I have some items, let's say the first, second, third, and I have its copies. Right, it has some copies. Let's say its copies is 2, and for this it is 3, and it is a 1 copy, right? So instead of having this much items, what you can do is that you just you just find the like value for the what, like case of the bounded knapsack, but with like you just divide it. Okay, so now instead of this, you have this case. Okay, the items, you have this first item 2 times, you have the second item 3 times, and you have this third item 3 times. And now it is again just bounded knapsack, right? You can take this or not take it. You can take this or not take this. So yeah, this is something like that. So yeah, you just divide it in the elements. This was the first approach. So like what you do is that, let's say which is nothing. So like I have 2 copies of first item. Okay, I have 2 copies of first item. But instead of this, what I do is that I just assume that I have 2 different books. Yeah, that's it. But and now either I can take first book or not take, and I can take second book or not take. So nothing to see with this copies. Okay. So like for each, I break it in several copies. I mean several books. So that's it. So that may be the simple and most fundamental approach. But again, this will give you a TLE, because yeah, let's say the copies can be till a pretty much big value. So what is the other case? What is the other thing? What is the other thing? So the other thing is nothing but you just do this thing, okay, and you will understand this thing. So let's say number of times taken. Times taken into Here it is just j, and just a second you are going to understand this stuff. Times taken into, okay, this is it. And here there should be another thing which is times taken is less than k of I. Okay, yeah, so what I did is that I just check for, I'll run a loop and let's say I check all of the possibilities, right? So like here from the first I element for if the sum should be equal to j, and like I take all of the possibilities. So like for the current element, for the ith element, what are the all of the possibilities? So yeah, the thing is that okay, just see here. Okay, yeah, let's say here that the item 2 has copies equal to 3. So the other the all of the possible case are that I take it 0 time, 1 time, 2 time, or 3 time, right? So yeah, I just do the same. I just check what if I take the current element 0 time? What if I take the current element 1 time? What if 2 times? What if 3 times? That's what I do here. So like first this is the case when I don't take this current element, then here it is just time taken. So until this times is less than equal to k of I, which is the limit on this, right? And this j minus times taken into this thing is greater than 0. What does it mean? So like if my capacity of my bag is just let's say 10 kgs, but at some case I this time taken into the w of I, right? The weight of my just current element is bigger than the capacity, then I don't take this, right? So yeah, this thing should be less than equal to j, right? So that's it. So yeah, this is the case. This thing is less than equal to j. So like this thing also cannot be more than j. And this is plus time taken, and I just check that if I take this as this much time, so then from the okay, I did a small mistake. Sorry. So from the I minus one element, what is the max value I can get? And then this is the extra value this is the value I get from taking the ith element. So that's it. But now again, like you can see that the time complexity is going to be huge, right? Because there are three loops. So the one loop is going for the number of elements, right? This is n into this thing is going for the sum, and this thing is the number of time I can take any value. So yeah, if let's say the weight is 1 for some value, then this thing is nothing but the number of maximum capacity. So yeah, this thing is O of so yeah, the time complexity here is O of n cross sum, where the sum is nothing but sum is equal to the sum of weights. Okay, so yeah, that's it. So again, like go this thing is pretty high. So like if in some question, what is the you have to see what is the range. I mean, so like in this case, you can solve this thing because yeah, 1000 into 1000 into 100 would be maybe less than. Okay, just a second. So n is still 100 and this thing. Okay, so you cannot, yeah, you cannot, I guess, solve this, because let's say if each item has the weight is equal to 1000, okay, and there are 100 items, then the sum is going to be alone, like the maximum sum is going to be 1 lakh, right? So the so like according to like this, 100 into 1 lakh into 1 lakh will be a pretty big number. So now what should you do? What should you do? Okay, so like here comes important part, and my favorite part in this whole lecture. So like a very few people know about this technique, okay? So what we do here, like let's see, okay, and I will just analyze some test case, and you will you will understand what I'm going to say. So let's say, uh, just a second. Okay, so let's say if I have some item, okay, if I have some item, let's say let's call it item one. The weight of it, this one is wi, or let's just have it as equal to 2, and let's say the value it gives is 5, and I have 7 copies of it, okay. I have 7 copies. And now as we discussed in the first case, right, what we do is I just make a array where I have 7 different elements, and I just do the knapsack, right? So like this in this item, I don't think I have this item. I have array of 7 items, right? So like all item like this, 7 items are like this. Okay, that's it. And now it is the knapsack thing, right? Like for each one, I take it or not take it. I take it or not take it. So yeah, for each item, I do the same, and that's how I count the answer. Okay. So like if the copies were 7, I divided into 7 different books with some weight and some value. Okay. But instead of this, instead of this, the amazing point is called the binary splitting. So what can I do is that what can I do here is that I can divide like this. So it was a 7 copies, but instead of this, I divide it into 1 copy, 2 copy, and 4 copy, like 3 books. So let's say, I mean, let's say I have this like type of 7 copies, right? 1, 2, 7 books, okay. So instead of just 7 books, and like I don't know how much book I have to take, okay. I can take only 1 book, or I can take this 2 books, I can take first 3 books. So like as many as I can, but instead of this thing, what I do is I break it into some bunch, okay. 1 book, then 2 book, and 4 book. That's it. And now either the whole thing will be taken or the whole thing will not be taken, okay. Whole thing will be taken, whole thing will not be taken. That's it. So like in this one approach, what I do is that I just split it into seven books, okay. 7 different books. So there are the 7 different books, and like for each thing I check if I take or not take or not take. That's it. But here I just divide it into the binary bits or binary digits, and now I will just take or not take. I just do that, okay. So now how this thing will be work, how this thing will work. So let's say the solution was like I just have to take the 1 book from it. So yeah, in this one also I can take. So the approach is like from this binary numbers I can make the every number from 1 to 7. Like, are you agree or not? Like, right, because I can make the every number possible. Right, I can make 1. This is just 1. I can make the 2. So I just take this and I got 2. I can make this 3. It's like I take this one and this one. And now number of copies is equal to 3. Let's take this one 4. I can take this one. Let's take about this 5. So I take this both, and now the number of copies is equal to 5. So the only the case is that instead of, I don't have to like break it into the 7 books, I can just break it into the books like this, and now every case would be solved, right? So that is the case, and so like what I do is that I just break it into the binary components, and that's how I can find the answer. Okay, so now let's say each component. Okay, so let's say the number is 16. So how it is going to be broken? So it will be broken in 1, 2, 4, 8, and 16 parts. That's it. So like you can see that for some number n, the number of broken parts is a log n. And like on this, it was the limited knapsack, as I was saying. It is like I can take it any number of time, but it is now on this, it is just the basic bounded knapsack. Like what I mean by bounded knapsack is just like I can either take this one or not take this one. I can either take some or not take some. So yeah, that was just the okay. Yeah, so this 16 will not come here. Okay, and this is, hold just a second. Okay, yeah, this will be the case. So now like it is, I have broken it into the binary components, right? And mhm. So like from this thing, like here I have to choose all possibilities, right? I can take it 2 times, 5 times, 7 times, 8 times, 9 times, so much time, like how much I want. But here, like this parts, I just have to check if I want to take them or not take them. If I want to take it or not take it. The case is just for one time, and each sum will be counted. Like for each case, it is going to be counted. So that was it. Like maybe like you can learn this on Codeforces blocks or somewhere. So like now you can see that there are only log n parts, right? Log n parts. So now that it is going to be around like O of n cross maximum sum cross log of maximum sum. Or let's say log of capacity. Okay, this is a better word. This is let's remove it. This is also capacity. So now you see that it is going to be give you a right answer for this. It will not give TLE because n is till 100 and the capacity can be till 1e5. So yeah, the code is going to be like O of, I mean, it is going to be do 1e7 operation, which is acceptable. So that's how we are going to solve this thing. Okay. Now this is again a nice question, and I give you this question for a homework. So like please take some time and think. So this is just the basic knapsack question, and but instead of DP of I comma W, you cannot use it because the W are till 1e9. So you have to think in some other way. Or let I just give you a hint. So like in this question, the question is same, right? The capacity is W, and sum of weight can be at most W, and you have to find the maximum possible values. But here the problem is that weight is pretty big. So like you have to make the DP as DP of I comma V, where I is the index and V is the value you get, and you have to like make find some transition. Like okay, let me just give you a smaller hint. So in this question, it is going to be DP of I comma V, which is equal to from the first element, sorry, first I elements. If we want the value is equal to V. What is the minimum weight? Minimum weight. Minimum weight we should have. So yeah, that is the state. And now it is interesting to find the answer for the uh, find the transition. So it is a like pretty nice question. Okay, it is going to be slightly tough, but yeah, if you can solve this, you can you will learn how to find the transition and states, right? So like in this type of question, the states are easy because you know that the I is index is going to be a one state, okay, and what and by just looking at the constraint and something, you will just try the some states, right? So let's say you try dp of I comma w, but then you will see that w is still 1 in 9, so you cannot use it. Then you will see can I make this value as a state? And then you will try to find the transition. You will find that, and if you cannot find, you will try to find some other state, something like that. But again, it is a nice problem, so try it. Okay, now we just move to the another interesting topic, which is called subset dp. Sorry, subset sum dp. Yeah, it is nothing but it is just that we have some coins, okay, and we have to find all of the money sums we can make using that coin. So it's like I have this coin of one of 2 rupees, 2 rupees, 4 rupees, and 5 rupees, and now I want to I want all of the combination of money I can make from these 4 coins, and I have to print that, right? So let's say I take this 2 coin, 2 and 5. So now my sum is going to be 7. I take this 4 and 2. Now my sum is going to be 6. And let's say I ask if I can make the sum is equal to 3, and I will see that I cannot make the sum is equal to 3. Can I make the sum is equal to 10? And I will see again that I cannot make the sum is equal to 10 something. So yeah, for each I have to output all of the possible sum I can make. That's it. So yeah, this is like a nice question. This is a pretty fundamental question. So if you don't know the solution for this question, it is going to be very tough to find the answer. But again, you know that this playlist is about DP, so this should be also be done by DP. So again, pause and try to think if you can solve this by DP. Okay. So this thing is simple. So in this, how do we solve is that let's just take this test case 2 2 4 4 5. Oh, so we have this money sum. So now, what are the observation we can get? So the smallest sum I can make is just take the smallest value, right? So okay, so first thing is let's say we will have it in the sorted order and find the smallest sum or the smallest value. So the smallest value is just the let's have the smallest sum here. Smallest sum. So it is just the smallest value of array, right? And what is the biggest sum you can make? So yeah, it is again easy. You just take all of the coins. So it is just the sum of all coins, right? And now in this, you have to find something. So let's just try to think it with making DP or what. Maybe let's just try it with a brute force one. Okay, a brute force one will be nice. So let's say from the first n elements. Okay, from the first n elements, you want to make the sum is equal to x. Now why not? Let's say the sum is equal to, okay, let's say sum is equal to 8. Okay, yeah, you want the, and yeah, by this brute force approach, everything will be clear to you. You want sum is equal to 8. Again, there will be two options, right? Either you take this last element or you don't take this last element. So let me just remove this. Instead of n, I just take 4 elements. Okay, so like first 4 elements, I want to make sum is equal to 8. Now I can take the fourth element or I can not take the fourth element. So if I take this fourth element, then I know that the the sum 5 is just done because I have taken the fourth element, right? So now, like from the first 3 elements, I just have to find if I can make the sum is equal to 3, right? So here this thing will like from the first 3 elements, can I make the sum is equal to 3? And this thing will be from the first 3 elements, can I make the sum is equal to 8? So this thing will now again ask two questions: if I take the third or not take the third. Here also, if I can take the third or not take the third, and like something like this. Again, you can see that this thing is will grow exponentially. Okay, why not just calculate? Why not just let's just make all of this thing. Okay, so here, let's say I take the third. If I can, okay, I so like this thing will be false. I cannot take, because yeah, the maximum, the sum I want is just 3, and if I take this third element, it will be 4, so it will exceed the sum I want. So this is I can do. And if I not take, then it will be like from the first I is equal to 2, I want that sum is equal to 3. Okay, sorry, right. And here if I take, so I is equal to now sum is equal to 4, right? Because like initially the sum was 8, I have taken the third element, so now the sum I want is just 4. And here if I don't take this, then I is equal to 2, and the sum I want is only is 8 now. Again here it will be also two parts: if I take the first element or not take the first element. So let's say if I is equal to 1, and now sum is equal to what? So if I take this one, so now the sum will be 1, and here if I not take the first element, because yeah, the first element, the sum is 2, I mean the value is 2. So right, and I is equal to 1, and now the sum is 3. Here also two parts: I is equal to 1, sum is equal to 2, I is equal to 1, sum is equal to 4. Here also two parts: if I take this second one, then I is equal to 1, sum is equal to 6, I is equal to 1, sum is equal to 8, right? So now like the thing is asking like from the first element, can I make the sum is equal to 1? I cannot make it. Can I make the sum is equal to 3 from the just first elements? I cannot make. I can do this thing. So this thing is true. So like there is some way to make this thing. So it is also true. It is also true, right? Because I can make like from the first element, I can make the sum is equal to 2. So that means that from the first two elements, I can make the sum is equal to 4. So that means that from the, okay, yeah, from the third element, I can make the sum is equal to 8. So that means that from the first 4 element, I can make the sum is equal to 8. So that was it. So now you can see that it is like growing exponentially, but you can have the states as just two elements, right? One is I and other is the sum. So it is like dp of ij, dp of I and value. Let's have it as call it as a sum. No, that's just value. Okay, that is nothing but if you can make sum is equal to value from first I elements, that's it. And now again it is just the simple thing. Okay, so like dp of I and well, it will be nothing but you don't take the current element, so it will be dp of I minus 1, or wait just a second, like it will be 1 or 0. Okay, it will be 1 or 0 because this thing is just true or false, right? Because it asks that if you can make it or you cannot make it. There is nothing to just minimize or maximize. There are only two cases, true and false. Okay, so true is just 1 and false is equal to 0. This thing will be 1 if what, if dp of I minus 1 j, I minus 1 val is equal to 1, or dp of I minus 1 and well minus v of I is equal to 1. So what is this thing is saying? So like you can make the sum is equal to val, if from I minus 1 you can make sum is equal to val. So this is the case of not take, which means that we don't take the current element. And this is the case of take. So which means that from now, sorry, this should be I minus 1. Okay. So like I have taken the current element, So now from the I minus 1 element, only this value is remaining. So if from the I minus 1 element, I can make this much value, I can make this much sum, then I will take the current one, and now my sum is just will be equal to val. So if I can do this thing or I can do this thing, then my dp of I val, I can make also this thing, right? So this thing will be 1. So that's it. So this is like now the transition is very easy, and states are also very easy. So like I hope that you understand this thing. Okay, now how the code would look like for this, it is again very easy. So yeah, the code is just the code of the knapsack we talked about. Okay, and just give me a second. Okay, yeah, so like the code is similar to the bounded knapsack, like the first example we solved, right? So just let's find what was the code for the first example. Okay, I guess this was the code for the first example. Okay, so now if I can make this, then it is true, or yeah, I have to do the or here. Okay, because like you know what the or operation does, right? So it will be I minus 1 and what the j minus w of I, that's it. So yeah, this is just the code. Okay, now there is also another optimization you can do. Okay, so the time and space complexity of this thing will be like O of n cross sum, right? Both the time complexity and the space complexity, because you have an array of this n cross sum, and like each operation is just done by in O of 1. So therefore, like there are n cross sum tables, I mean elements of the table, and each element is calculated in O of 1 time. So the time complexity is also O of n cross sum. but you can optimize it with the bit set. So like for the bit set thing, you can learn it from my bit manipulation video on this code hurdle. So like by using bit set, the time complexity and the space complexity both reduce to O of n cross sum divided by 64. And although this 64 on the only change is that instead of the integer we use a bit set this thing, okay, sorry, this bit set only. And like this is just the small minor change of one line of one data structure. So bit set is an inbuilt data structure in the C++. You can see it in my bit manipulation third video, I guess. And the time complexity reduces by this much. So this is a very important technique. Okay, let's say if you're maybe like the n and sum are till maybe like 1e4, then 1e4 into 1e4 will be 10 raised to power 8. That can give you a TLE. Or maybe there are many questions that requires bit set. Like if you just solve them manually by this method, you will get TLE. But if you reduce it to now, you will get accepted. So this is an amazing pattern you must learn. So like I request you to see that video of my the bit set one, and yeah, this thing can be used like solve with this easily. Okay, so try to solve this question by the simple method and the bit set using bit set also. And now comes to the like amazing question, which is like the toughest but the best question of this playlist. Okay, so if you can solve this question, after that I guarantee you that the the 90% of the DP question of knapsack will be done by you. Okay, so try to solve this question. So this will be homework for you, and if you cannot solve this, then in the next lecture I will explain it. So but you must solve this question. Okay, so yeah, the name is round a subset on Codeforces. So okay, that was it for today, and meet you in the next lecture.